we are discussing is electrochemical aspect of redox reaction. Aspect of redox process or redox reactions. Okay. So in class 12, you will have a one complete chapter on this. So what we will be covering in redox chapter in class 11, that will be a very brief introduction to electrochemistry. Electrochemistry is a separate chapter in class 12. What is this electrochemistry? This is basically a branch of chemistry that deals with interconversion, branch of chemistry that deals with interconversion of chemical and electrical energy. Chemical and electrical energy. Okay, so we can convert an electrical energy to chemical energy, electrical to chemical, and then from a chemical energy we can also generate electricity or electrical energy. So electrical to chemical means some process which are not very feasible, but by supplying electricity we can run those processes. So this is how we can convert our electrical energy in the form of chemical energy. So let's say we have a substance A and its energy is E1, and we want to make a substance B, its energy is E2, and E1 is less than E2. Okay, I'm telling you in a very simple language right now. Okay, these terms will be explained to you in great detail in class 12. So E1 is lesser. So let's say A is stable, but we want B, which is of higher energy. So naturally this A will not convert to B because this is the law of nature. The lesser energy any substance is having, it will have more stability. But if you want to convert A in the form of B, then we have to store E1 minus E2 or E2 minus E1 energy inside it. Then it will become B. The energy gap which is there, that we have to fill up. So what happens? We supply the energy in the form of electrical energy. The gap is here between E1 and E2. A is at lower energy, B is at higher energy. A was stable, but we wanted A to convert to B. If we want A to convert to B, we have to supply energy. And that energy we can supply in many forms. Sometimes we give heat. With the heat also we can do the same process. And we can also supply electrical energy. Then A can convert to B. Now where is the energy gone? Energy will never be lost. Energy will never be created. It will just convert from one form to other form. So this energy is now stored inside the B. So when this is stored inside a compound, we call it chemical energy. So what we did, we converted a compound A or a substance A in the form of B, which was of higher energy. We supplied the energy in the form of electrical energy, and now we have B. So let's see some chemical reaction. You may not be familiar. Just take a note of it. For example, water, H2O liquid. Highly stable compound, it can be converted to hydrogen gas and oxygen gas, which are highly reactive gases. How is this possible? This is possible by a variety of methods. And one of the method is electrolysis, means supplying electrical energy. So where will that energy be gone, which will be supplied? That will be stored inside S2 and O2, which are more energetic compounds. So what we are doing, we are converting our electrical energy into chemical energy, or our electrical energy will be stored inside which are of higher energy. Is this thing clear? This is what we mean
Yes.
by converting electrical energy to chemical energy. Okay. And similar way, what we can do, sometimes we take some high energetic chemicals. Let's say we take C. So this chemical C is of high energy. Let's say its energy is E4. And it can become a chemical D. Its energy is E5. And E4 is greater than E5. So C can naturally come and become D. C can naturally become D because E5 is lesser and E4 is greater. So from high energy, it can come to lower energy. So where will this energy be gone? The energy which was stored inside the chemical, that will be lost. And this energy we can harness in the form of electrical energy. The energy which will be lost in this process, in a natural process, when a substance of higher energy converts to lower energy, then stored energy, chemically stored energy, can be converted to electrical energy. So otherwise, means chemical to electrical is also possible. So electrical to chemical also we can do, and chemical to electrical also we can do. Chemical to electrical, you have seen many applications like batteries and cell, batteries, right? What is there in batteries? There is a chemical stored, and that chemical can naturally convert from higher energy substances to lower energy substance, and energy is released. And the same energy we use in the form of electrical energy. Okay? All the batteries have certain chemical. If you see your inverter battery, that is also called lead storage battery. More detail of battery will be explained to you in class 12th. But right now I'm telling you in very simple language, electrical energy to chemical energy and chemical energy to electrical energy. This interconversion is called electrochemistry. And very briefly, it has been explained in the redox chapter as the last topic. So what we will cover today, electrochemical aspect of redox reaction. So we will see the second case, this case, chemical to electrical. How a energy stored inside a chemical can be converted in the form of electrical energy, or how does a battery work? This I will explain you, okay? Which is given in your notebook, in your textbook, school textbook, in the form of Daniell cell or galvanic cell. It is explained in the form of galvanic cell or Daniell cell in your school textbook. Okay, that how a battery work and how a redox process happen, and then we get the electrical energy. Okay, let's see that. Now to construct a battery, what will battery do? Battery will do this, chemical to electrical. A chemical energy will be converted to electrical energy. Okay. Now chemically stored energy need to be converted to electrical. So what should happen? Some natural process should happen. If we had done thermodynamics, I could have explained you in a different way. These natural processes are basically called spontaneous process. So one spontaneous process will happen, or one natural process will happen. A chemical will convert from one form to other form, and the chemical which was previously present, let's say this was previously present, let's say this is a reactant, and this will convert to product. This reactant is more energetic, and this is less energetic. And this process, energy loss will happen, and that will be converted in the form of electrical energy. Now, what is the redox point of view here? Why we are saying electrochemical aspect of redox? This will be very well understood by you in few minutes. Okay, so we will see this thing. How does this happen in a redox process? How inside all batteries some redox process is happening, and how we are generating electricity. Okay, we'll talk about the construction of a battery. So any battery, let me mention here one thing, that batteries are combination of cells. Did you know this thing? What we call battery? Batteries are basically combination of cell. Okay, like you can have 9-volt battery. So for 9-volt battery, you can have 3 cell of 3 volt, 3 volt, 3 volt, 3 volt. You might have seen that also. Like in your TV remote, you might have seen more than one cell is kept, and each cell is of 3 volt. Right? So single unit is cell, and combination of cell is called battery. Okay, you might have observed that the battery which we use inside the TV remote, we call that as a cell because that's a single unit. Okay, but what you use as a what you use for inverter, that we call as a battery because there are multiple cell fitted inside it. So battery is basically combination of cell. Multiple cell makes a battery. So how does this work? We need to look for some spontaneous process or natural process. In that process, some energy will be released, and that will be converted to electrical energy. In your syllabus, we have galvanic cell. So I will talk about that. Galvanic cell. It has 3 parts. First part is oxidation, half cell. Second part is reduction, half cell. And third and most important part is salt bridge. Salt bridge. Okay. So let's see what is the role of these 3 parts and how all together will make a cell. Oxidation half cell. Oxidation half cell means oxidation process will happen here. And oxidation means loss of electron will happen here. In the reduction half cell, reduction will happen, or means gain of electron will happen. So electron will be lost from one side and it will be gained on the other side. So basically electron will move from this part to this part. Electron will move. And if we can move the electron, movement of charge is happening. When does movement of charge happen? You have learned in physics. Charge will move when there is a potential difference, right?
Yes, sir.
Charge move from one point to other point A to B when there is a potential difference. That means we will be able to establish a potential difference. If we are able to establish the potential difference, that means we are able to generate electricity, correct? 2 volt or 4 volt, whatever. So this is what we will do. Okay, we'll explain the whole thing. So oxidation half cell. So any of the half cell will consist of 2 parts. One part is electrode, other part is electrolyte. To construct it in your lab, we take a beaker, and in that beaker we immerse one metal piece, mostly metal piece, because in non-metal we just have one option, graphite. This thing is called electrode, and we will fill one solution inside, which will be called electrolyte. Our electrode should not react with electrolyte. That's the one condition. Our electrode should not react with electrolyte. So to avoid it, what we do, let's say we are taking this electrode of zinc. Then we can take the zinc salt itself as electrolyte. So zinc will never react with zinc ion. Correct? Will zinc react with zinc ion? No. Zinc can react with other ions. But why will zinc react with the zinc ion itself? It's like two different states of the same zinc. You have learned in the class 10, if you have, let's say, iron and there is a cupric ion, copper sulfate is there, then what will happen? It will become ferrous sulfate, Fe2 plus sulfate ion, and this cupric will become copper. So basically what happened here, iron has given electron to cupric ion, and this was +2, it became 0, and iron from the 0 has become +2. So this electron transfer start happening depending upon the reactivity of the two elements, and we don't want these kind of conflict here. So that's why we are keeping the same metal and metal ion inside here. So to avoid the conflict, the best thing is take the same metal salt. There is no other reason, okay? If we can avoid the conflict by taking different electrolyte, it is also possible. Since this chapter will not be explained in too much detail in class 11, that's why the examples are also taken like this. So we have taken the metal zinc, and we have taken some metal salt. It's an electrolyte, so it should be charge carrier. Our charge carriers are zinc ion and sulfate ion. And since they are in aqueous state, that means they are not binded with each other, rather they are surrounded by water molecules. So they are free to move, zinc ion and sulfate ion. They can conduct electricity. If it was zinc sulfate solid, then those ions were not free. Ionic compound cannot conduct electricity in solid state. Only when they are separated, they can do that. We have to take another setup. A very similar setup. Again, we will take one metal. Let's say this time we are taking copper and one copper salt. Let's say cupric sulfate, Cu2 positive and sulfate ion. Now metals have tendency to lose electrons. So zinc want to lose electron, copper want to lose electron. And if we add these two with one wire, one metal wire, then zinc want to lose electron, zinc want to convert to zinc ion. It's a metal, it has tendency to lose electron. Copper also want to lose electron. But if you look at the reactivity series, more than copper, zinc want to lose electron, or zinc has a higher tendency to lose electron. So between zinc and copper, more reactive metal is zinc. So effectively, zinc will be losing electron. But reason is not that simple. When zinc is losing electron, these electrons are reaching this plate. Let's say zinc lost electron. And look at the path of that electron. This will try to reach here. And this will reach copper. So can copper gain electron? Never. No metal ever gain electron. Okay. Metal may be more reactive or less reactive, but metal never gain electron. And this electron will eventually come inside the solution. Then somebody need to gain electron. If no one is gaining electron, then zinc cannot keep on losing electron. Some receptor should be there. So here in the solution, we got cupric ion, which can gain electron and can become copper. Because Cu2 positive ion, okay, that is not very stable. Copper itself is stable. That's why it is not like to lose electron very much. Why copper has low tendency to lose electron? Because copper itself is quite stable. It is not very reactive. If you remember, there used to be coins made of copper. Copper is one of the coinage metal. Means it is not very reactive. So even if we had lost electron earlier, it is in the form of cupric ion, it will love to gain back electron. Now what about the copper? If copper was wanted to lose electron, then electron has to go this way, opposite side. Exactly opposite. If copper want to lose electron, then these electrons has to travel this way. Zinc obviously will not gain electron, no metal gains electron. Then in the solution we got zinc ion. It has to gain electron, and which is not feasible because zinc like to convert to the zinc ion. Zinc is very reactive metal. So zinc ion is not going to convert back to zinc. So when the moment you add it, okay, the moment you add it, you will see that electrons started going from zinc side to copper side. These electrons will move from the zinc side to copper side. There is a flow of electron happening or flow of charge happening. That means there is already a potential difference established. You can also tell there is a direction of current from copper side to zinc side, which will be just opposite to the flow of electron. So this is happening. Electrons are moving from zinc to copper side. Zinc losing electron, becoming zinc ion. And cupric ion in solution, gaining those electrons and becoming copper again. But there is a big problem that this cannot happen for a long time. Can anyone tell me why this cannot happen for a long time? Anyone? Raise your hand if you know it. That this process will stop soon after it starts. No one? Okay, it's okay. Yes, Kalyani.
So I can guess. Is it because of chemical equilibrium will be achieved and then the
Very good try.
copper
Okay.
won't?
Not exactly that. Okay, it's a little different story here. So story here is that zinc, when zinc is losing electron, then zinc ions are being generated, and those zinc ions are trying to come inside the solution. They will come inside. And when they will come inside, this solution will become positive charge. Why it will become positively charged? Because of excess of zinc ion. Earlier, there were equal amount of zinc ion and sulfate ion, but if zinc loses electron, then electron will go this way and zinc ion will come this way. So when they come to the solution, this solution will become positively charged. And when it becomes positive charge, it will not allow more zinc ion to come. So more zinc ion will not be accepted because solution will get positively charged. Positive charge will be accumulated over here and it will refuse to accept more zinc ion. Positive will start rippling. So when there will be a repulsion, So zinc ion will not be very much welcome. But that's not all. Even if you look at this side, cupric ions will start disappearing. Cupric ions are gaining electron and are becoming copper. So you will see one coating of copper coming over here. Cupric ions are converting in the form of copper. So this solution will have less amount of cupric ion now, and this solution will become negatively charged. Why negative? Because cupric ions are leaving the solution. Earlier there were equal amount of cupric ion and sulfate ion. Now cupric ions are leaving solution and becoming copper. So solution will be having more sulfate and less cupric ion. More sulfate means solution will become negatively charged. So the moment solution become negative charge, now electrons which are reaching the solution will not be welcome. So even this electron will not be welcome, and solution will become negative charge. So the origin of both the thing, electron and zinc ion, both will stop. Zinc will stop losing electron because electrons are not accepted, electrons are not welcome on right hand side, and zinc ion is also not welcome in the left hand side. So this process will start and will stop. Is this thing clear? If not, please ask me. I can explain one more time. Okay, I hope you understood. Now to take care of this problem, we will add the third component of the cell, which is called salt bridge. Okay, I will explain that separately, and then I will bring it to this slide again. Now, what is the salt bridge? Salt bridge is a U-shaped glass tube. It's a glass tube. In this glass tube, we fill one electrolyte, which is a neutral electrolyte. Now, what is the meaning of neutral here? Neutral means it should not react with any electrolyte present in shell. So be that oxidation half cell or reduction half cell on any side, any ion present should not react with it. So we use the ions which are not very reactive, like K plus ion. K plus will not react with anything. K plus itself is highly stable. Cl minus ion, highly stable. So these ions are highly stable, so we can use KCl as a good choice. Or similarly, we can think of the ions which are not very reactive. And ions should also be smaller, but that's a lot of detail. It will be taught to you in class 12 about their ionic mobility and all, how fast the ions can move. But general idea is ions should be smaller. When they are smaller, they move faster. So conduction is superior. We need to have one electrolyte over here, which should not react with anything else. So neutral electrolyte is required. We can fill the neutral electrolyte over here, but the problem is this glass tube we will be using in this format, in the inverted format. We will immerse it on both the ends. So when you try to do it, the whole solution will fall down. It will fall down. And how to hold the electrolyte inside this glass tube? For that, we want to hold the entire electrolyte inside this glass tube without electrolyte getting outside this glass tube. We use one substance. Its name is agar agar. Agar agar. This one is an organic compound. Organic compound. And the feature of this compound is its melting point is around 40 degrees Celsius. So what we can do? We can take agar and put it in the oven, microwave, and we can just put the entire agar. So if the temperature will be more than 40 degrees Celsius, then agar will become liquid. And once agar become liquid, listen carefully. Once agar become liquid, you will mix it with our KCl solution. So KCl solution will fall down, but if you mix KCl solution with agar, it's a gelatin-like substance. It can very well mix up with KCl. So KCl and agar, this mixture will be created. And then this mixture we can fill inside this glass tube. And as soon as temperature will go below 40 degrees Celsius, agar will become solid again. Agar will become solid. This time agar was liquid at more than 40 degrees Celsius. So it will become solid again, and this will hold the entire electrolyte inside this glass tube. And now even if you invert it, it will not fall down. So what we have done, we have taken organic substance agar. Its melting point was 40 degrees Celsius, so we can easily heat it above 40 degrees Celsius. And after that, we mixed it with our KCl solution. And then once the temperature get below 40 degrees Celsius, means room temperature, it will become solid. So this agar will hold our electrolyte here, neutral electrolyte inside it. So now our bridge is ready. Yes, Kalyani.
So does the agar not react in the
That's
reaction?
organic substance, it will not react. Okay. So our salt bridge is ready, and we will bring it here, and we will put it inside. We will put it over here. Now the salt bridge is filled with KCl. And now how this will help? So see this carefully. The moment one zinc will become zinc ion and will lose electrons. So zinc ion will come to this solution and will make this solution positively charged. As soon as this solution will become positively charged, it will attract the negative charge ion from salt bridge. So which one is negatively charged ion in salt bridge? Cl minus ion. There are two kinds of ion, K plus and Cl minus. It will attract the negative charge ion Cl minus ion from salt bridge. So Cl minus ion will come to the solution. So one extra zinc ion came. For every extra zinc ion coming to the solution, 2 Cl minus ion will also come to the solution from salt bridge and will make the solution neutral again, so that more zinc can come. Let's talk about this side. What was happening on this side? One cupric ion was disappearing. Cupric ion was gaining electron and was disappearing from the solution. So this side is story. Cupric ion was gaining electron and was becoming copper. So we were having extra sulfate ion now. Cupric ion was gone. Extra sulfate ion we were having. Now this extra sulfate ion will attract the positive charge from salt bridge, and 2K plus will come this time, and this side solution will also become neutral. So when neutrality is maintained, now zinc is free to lose more electron. Electrons will come to this side, and zinc ion can come to this side, and solution will remain neutral. So a continuous passage of electron is possible from zinc to copper side. Is this thing clear? Please ask me question if you have any. After that, I will explain you a few more things. If you could not understand any part of it, please ask me. How the continuous flow of electron is maintained in this arrangement. No question? Okay. We can put some galvanometer or voltmeter. Have you heard of galvanometer? Galvanometer. Galvanometer will have a needle, right, which will be at 0 if there is no current flow. It will move this direction if there is any current flow. So you can put the galvanometer, you can see that current is flowing here.
Sir,
So zinc is, yes please, any question?
so what will happen to sulfate ion? Will just stay
Sulfate
there?
ion is doing nothing. Sulfate ion is just attracting the K plus ion from salt bridge.
Okay.
Because we got extra sulfate, right? Cupric is gone. Earlier we had equal amount of cupric and sulfate. Both were neutralizing each other. The moment cupric become copper, so we have lesser positive charge, right? Or we can say we have extra sulfate ion. So extra sulfate ion will attract K plus ion from the salt bridge, and it will become neutral again.
Yes, sir. Thank you.
So both side neutrality is maintained after adding the salt bridge. We can also put a voltmeter to measure how much is the potential difference. We can also put an ammeter to measure how much is the current flowing. Voltmeter, ammeter, or galvanometer, anything we can put. So reading of voltage and current is not important here. Important thing is how a continuous flow of electron is possible. Over here, what is happening? From one side, electrons are being lost, other side, electrons are being gained. So one side oxidation is happening, other side reduction is happening. So this zinc side, where we see the loss of electron, this is oxidation. And copper side, we are seeing a gain of electron. This is reduction. So left side is our oxidation half cell, right side is reduction half cell. And wherever oxidation happen, that electrode is always called anode. Okay, if you have learned that positive plate is anode, that's wrong. The anode is the electrode at which oxidation takes place. That's the correct definition of anode. Anode is the electrode at which oxidation takes place. And wherever reduction takes place, that is called cathode. This side is anode, that side is cathode. In fact, anode this time is negatively charged. How anode is negatively charged? I will explain you. But before that, if you have any query, please ask me. Okay, I hope you understood. So I will explain you how the anode is negatively charged this time. Please take the screenshot or keep on taking notes. Okay. So we have to understand the chronology of the event. Zinc is losing electron and zinc ion is coming to solution. When zinc ion come to solution, it will attract Cl minus ion from salt bridge and it will become neutral. But the moment the Cl minus ion will come to solution, more zinc ion will also be there. And this will also attract the Cl minus ion. Right? So there will always be some positive charge in the solution because at first zinc ions are coming and then they are attracting Cl minus ion. It's not the other way around. So this solution will always remain positively charged because zinc ion will be here. It will just not be accumulated. Because as soon as zinc ion is coming, it is attracting Cl minus ion from salt bridge and becoming neutral again. But some extra zinc ion is always there. So this solution became positively charged. It will remain positively charged, not too much positively charged because positive charge will not be accumulated. Similarly, since electrons will be present on the plate, once zinc loses electron will be present on the plate all the time. They will be always accepted on this side, but there will be some electron present on the plate also. So this plate will be negatively charged. This plate is negatively charged. This solution is positively charged. Now let's check on this side. So cupric ions are disappearing. So we have extra sulfate ion here. And this extra sulfate ion are attracting potassium ion to become neutral. But always we will have at least one sulfate ion extra. We will have some sulfate ion extra, not one. Some sulfate ion will always be there, which will wait for K plus ion to come. Once they come, they will become neutral. But by the time they become neutral, some cupric ion will again become copper and extra sulfate ion will be left in the solution. So this way, this solution will always remain negatively charged due to sulfate ion. Why I'm saying so? Because in the solution we have cupric and sulfate. Cupric ions are leaving solution and becoming copper. So in the solution we have extra sulfate, which will attract the K plus ion from salt bridge and become neutral. But by the time they attract it, few more cupric will be gone and we will always have extra sulfate. So this solution is negatively charged. Similarly, there is accumulation of cupric ion on the plate, which are attracting the electrons. So electrons they are attracting. So at first they are reaching there and then they are attracting electron. So once they gain the electron, this plate will also become neutral. But by that time, some cupric ion will again approach the plate. So this plate will be positively charged because of cupric ion reaching this plate and then gaining electron. So after gaining electron, this plate will become neutral, but by that time, few more cupric ion will come. So cupric ion has a tendency to come over here and then becoming copper. So this plate will be positively charged, solution negatively charged. This plate negatively charged, solution positively charged. Is this thing clear? If not, please ask me. So now you in the physics you have learned. Have you learned the formula for the potential? V equal to KQ by R. Have you learned this formula or not? Tell me.
No, sir.
You haven't learned? Okay. Basically, it means that if there is a charge, there is a potential. Okay. Potential comes from the charge only. Okay. You can see from this formula that V is proportional to Q. More charge, more potential. But what if we have two different charges, Q1 and Q2? If Q1 and Q2
is this same as gravitational potential, like similar to that?
Similar to that.
Okay, sir.
If you have two different charges Q1 and Q2, then you will have two different potential V1 and V2, right?
Yes.
Correct? So same thing we can apply here. So we are seeing that our electrode is negatively charged here and electrolyte is positively charged here. So electrode and electrolyte both are having different potential. So when they have different potential, so we can say there is a potential difference between electrode and electrolyte, correct? Because they are at different potential, so there is a potential difference between electrode and electrolyte, especially at their interface, because there is a different charge. This plate is always negatively charged, solution is always positively charged. So their interface means common phase, will have a potential difference. And this potential difference is called electrode potential. So definition of electrode potential, if it comes in exam, you will write electrode potential is potential developed at the interface of electrode and electrolyte. Okay, and you can see here clearly that why there is a potential difference, because of different charge. Different charge means different potential means potential difference. So this side also you can see solution was negatively charged, plate was positively charged. So different charge, different potential, and there is a potential difference. So both sides we will get potential difference. Okay, and we are also seeing a continuous flow of electron. So this is how the redox process works in electrochemical reactions. So redox process, like zinc is losing electron, this is oxidation. Cupricine is gaining electron, that's a reduction. So if you write the reaction separately, so this can be summarized as zinc losing electron, this is oxidation part, and cupricine gaining electron, becoming copper solid, this is reduction part. Oxidation and reduction both are happening simultaneously. So this was the redox. So please ask me if you have any confusion in this. Those who have asked me for this topic, those who have voted for this topic, so which specific thing you have not understood? Or is there anything else apart from this you wanted to ask? Just raise your hand and ask me. How many of you have understood this? Those who are in the meeting? How many of you have understood? Okay. Quite a few have understood. Okay. How many of you have not understood? Raise your hand. How many of you have not understood? You need more clarity. How many of you have not understood? Just raise your hand. 2 or 3 students should be there. Those who have not raised their hand. Anyone? No one? Okay. So everyone understood. So shall I do the de-Broglie now or other class? What do you guys say? We got some 8-10 minutes. Anyone want to understand in 10 minutes? A brief.
So could you do it in detail later?
Okay, I will do in the next class also. In 5 minutes, I will just give the idea, okay?
Yeah.
I will do in detail in the next class. De-Broglie. So de-Broglie says that not just radiation, I'm telling you the exact thought. Not just radiation, all matter has dual nature. Keep in mind, radiation has dual nature. It was long back proven that particle and wave nature both are present in the radiation, right? Or what you have learned, light has a dual behavior. Light is also wave, light is also a particle. So de Broglie said that why just radiation? All the particles also, all the matter also have a dual behavior. So everyone was in a thought that, well, matter is a particle, solid, liquid, gas, those are particle. How come they are wave? How come they are wave? This was the question. De Broglie said, well, they are matter wave. Then everyone was still confused and asked that, what do you mean by matter wave? So there are two kind of wave. It will be taught to you in physics. Static wave or standing wave. Another one is moving wave. Moving wave means when particles of the medium, they move along the wave. And standing wave means they just simply oscillate along their mean position, they don't move. Like the wave which can be generated in string. So string particles are not going anywhere, they just oscillate. Then de Broglie gave the clarification. He said, well, standing wave. So matter wave is a standing wave. Then everybody questioned, okay, well, if all metals have this wave nature, they are standing wave, then why we are not able to observe it? Then de Broglie said, well, wave nature of matter is significant only for microscopic objects.
That means bigger objects have very high wavelength. That's why.
Very, very low wavelength. It's not significant.
Very high, no?
Sorry?
Very high wavelength, no?
Not very high, very low wavelength. It's not even measurable. I will tell that. Okay. That's the next question everybody asked de Broglie, that what do you mean by for microscopic? Why not for the macroscopic, larger object? Then he said, because of one relation, okay, which he got. He was a brilliant mathematician also, okay. His work was based on pure mathematics and statistics. His work was not based by some experiment. He just hit this jackpot and got this equation. Lambda equal to h upon p. So this equation was a groundbreaking because this equation simply relate a wave nature to particle nature. He said any moving object will have a momentum. This p is basically mass into velocity. If there is any moving object, it will have a momentum. And if it is having momentum, it will have a wavelength. So with this relation, it was evident that anything which is moving has a wavelength. But if you put it into the equation, you will get to know that how insignificant it is for a larger object. For example, if I take a cricket ball, let's say cricket ball is of 1 kilogram, and then there is a bowler who is throwing it at 180 kilometer per hour. So if I convert it to meter per second, how much will be that? 1 kilometer means 1000 meter, 1 hour 3600 seconds. Right? How much is this coming? 50, right? 50 meter per second. So there is a bowler who is throwing this ball, 1 kilogram cricket ball with 50 meter per second or 180 kilometer per hour. That's very high speed. Let's see if we see any wavelength or not. What will be the wavelength? Lambda will be equal to h upon p. So value of h is 6.626 into 10 raised to the power minus 34. Mass into velocity, I'm putting everything in MKs, that's why I converted to meter per second. Mass is 1 kilogram, velocity is 50 meter per second. Now just look at it. Wavelength we are getting, let's say this was not even 50, this was 100. Or I can just multiply with the 2 on both numerator and denominator. So numerator will become some 13.2 into 10 to the power minus 34 upon 100. Or we got 13.2 into 10 raised to the power minus 36 meter. You all know that the size of nucleus is 10 to the power minus 15 meter. Its diameter is 10 to the power minus 15 meter. And there are very few humans who are able to see all this because microscope of this precision are very, very rare. Those are called electron microscope. And this is trillion times smaller than that. Then how possibly we will be able to see the wave nature of this object? So when we take any larger object, then wavelength become insignificant. So we are not able to visualize the wave nature, but it is there. But for a microscopic object, let's see the microscopic object like electron. Let's say there is an electron which is moving in the first orbit of hydrogen atom. So in the first orbit, velocity is 2.18 10 raised to the power 6 meter per second. Let's calculate its wavelength, lambda equal to h upon p. H is 6.626 10 raised to the power minus 34 divided by mass of electron, which is 9.1 into 10 to the power minus 31 kilogram into 2.18 into 10 raised to the power 6. If we just work on power of 10, so we got minus 34 plus 31 minus 6. It's a minus 3 minus 6 minus 9. 10 to the power minus 9 meter. Somewhere close. Okay, even if it becomes 10 to the power minus 10, that is also 1 angstrom. So this wavelength, especially we cannot neglect for a particle like electron. Right? It is significant for electron if its wavelength is 10 to the power minus 9 meter because electron itself is quite small. The whole atom is very small, and if it is creating a wavelength of this dimension, it is very significant. The whole atom size is 10 to the power minus 8 to 10 to the power minus 10 meter. Whole atom size. And if the wavelength of a single electron is in this dimension, it won't be exactly that. We have to solve it. Then it is not insignificant. We have to consider it. So de-Broglie proven that it is wise to consider the wave nature for microscopic object, but not for the macroscopic. Then everybody asks, okay, well, you said electrons have a wave nature, then how do they move? Is Bohr wrong? Bohr is saying that they move in a circular path like a particle. Now, how will the electron move when it is a wave? So de-Broglie said that, well, Bohr is not wrong. We just need to visualize it differently. Let's say this is the first orbit. This is the second one. This is the third one. So these are the different paths where electrons is moving. Let's say we are talking about this path. I will make one more smaller one in the center. So de Broglie said that in the third orbit or in any nth orbit, like I'm taking the example of the third one, the movement of electron will be something like this. So there is a single electron which is making a three-wave pattern in the third orbit. And for the same, he has given one equation that n lambda will be equal to 2 by Rn. That circumference of the path, 2 pi Rn is the circumference of the path, will always be the integral multiple of the wavelength. Why it is mandatory to have an integral multiple? Because the whole circumference, it needed to be covered by an integer number of oscillation. But it was not integer number, let's say it was 3.5 or something. The circumference is being covered by 3.5 or something. If I draw one more case here, to draw 3.5, I have to take a smaller oscillation, 1, 2, 3, and then 4. So you can see that in this path we got waves cancelling out each other. So when wave cancel out each other, that means electron cannot be here. But in practical result, we have found that electron is there. There is a radial probability of finding electron everywhere. So if this is not some angular node, so how can wave cancel out each other? So this was like not consistent with the data which we have obtained. So the whole circumference will be covered by only an integer number of oscillations. It's not possible any other way. I will discuss this in detail in the next class. And I hope you guys understood something new. We will be keep on taking these classes. Please keep on posting. And if you have any doubt regarding what you learned today, please reach out to me. And if you need any further clarification, again, please reach out to me. I also have another meeting in some time, so I have to end the session. Okay, guys. Bye-bye. Good night.
Thank you, sir. Good night.
Thank you, sir. Good night.
Thank you, sir. Good night, sir.
Bye, sir. Good night.
Bye-bye.
Thank you, sir.
Welcome. Bye-bye.